AB Calculus 5.2, day number 1, approximating areas under a curve. Our goals for today, as you can see, are to make a connection between the area under the curve and the indefinite integral. Approximate area under the curve using the rectangular approximation methods, which we call Ram, and then connecting area under the curve with displacement and distance traveled. So the following figure or flowchart that you can see below summarizes our current understanding and raises a few questions. So we kind of know this left stem from our first semester work, that when we take the derivative of f of x, we get f prime of x, and the geometric representation of that is the slope of a tangent line at a given x value. To this point, we have also now learned what this notation means here with an indefinite integral. And if we add limits to this indefinite integral, for example, let's say we took this integral from x equals 1 to x equals 2, the geometric representation is the area under the curve f of x from x equals 1 to x equals 2. Now, I should be more specific. That is the area trapped between f of x and the x-axis. Okay, so let's look at a quick example of what this might apply to. So let's talk distance traveled, a little bit of basic physics. Consider a train traveling at a constant rate of 75 miles per hour for 3 hours. What is the distance traveled by the train? Okay, so we've got velocity and time. So let's say our time is in hours. And this is 3, 2, and 1 hours. And our velocity, of course, is constant in this case, which is in miles per hour. And we've got a train traveling at 75 miles per hour for the entirety of those 3 hours. So when it comes to physics, speed equals distance divided by time. And distance equals speed times time. Now recall that speed is the absolute value of velocity, which in this case, we're just assuming the train is traveling one direction for the entire time. So how could I find the distance traveled by the train? Well, assuming that the speed is constant, and we travel for a total of 3 hours, if we took speed times time, our distance would equal 75 times 3. That distance ends up representing the area underneath that curve trapped between the t-axis and the function v of t. Now, that's nice and easy to do when v of t is linear, but the problem arises when v of t is nonlinear. So total distance is equal to the area under the curve, as we can see, is 75 for 3 hours. When we accumulate instantaneous changes over an interval, this is the area under the curve, or what we'd call integral calculus. Now, we're going to consider in the slides following what to do if our velocity function is not constant. So we're going to do some approximation methods using what I spoke about earlier, which is this Lram method. All right, so let's go ahead and get into the details. All right, example 2, we're going to find the distance traveled when the velocity varies. So in this case, v of t is no longer going to be constant. It is going to be quadratic in nature. So let's read the example, and then we'll get into the details on how to calculate, or approximate, I should say, the distance traveled over a certain amount of time. A particle starts at t equals 0 at a position of 0 and moves to the right with a velocity of t squared for t greater than or equal to 0. Where would the particle be at t equals 3? Now, I'm going to read this little paragraph here. We don't have the tools to exactly calculate this yet, but we can make an approximation. And what we're going to do is we're going to divide this up into 3 subintervals. So I'm going to divide this up into this first interval from 0 to 1, a second interval from 1 to 2, and a third interval from 2 to 3. So what we're going to do is we are going to use what's called a left rectangular approximation method. Okay, so Lram stands for left rectangular approximation method. Now, that just means we're going to be calculating the area of a bunch of rectangles. We're going to add them up. Okay, so if you look at this first space, right, from 0 to 1, the area under the curve is almost triangular, right? From 1 to 2, it looks almost like a trapezoid, and then the same thing from 2 to 3. Now, we can get more detailed and actually more accurate with our approximations than this method we're going to use here, but I'm going to show you the basics of what's called the Lram method. So anytime you're prompted with an Lram method, you want to take these, in these 3 subintervals, I've got 4 points. Okay, and what we're going to do is we're going to start from the left, and we're just going to start drawing rectangles. Now, the first interval is going to have a rectangle that has a height of 0. Okay, so I'm specifically taking the left-hand output, right? So this output right here, and that's going to represent the height of my first rectangle. Okay, so you can think of this as 3 rectangles, the first of which, okay, so I'm going to say the area under the curve from 0 to 3 of v of t dt is going to be approximately equal to the sum of my 3 rectangles areas. Okay, so the first one would have a base of 1 and a height of 0. Okay, my second rectangle, I'm going to take the output of the leftmost point of that interval. Okay, of course, left Lram, I'm going to take that output for the leftmost point, like I said. Okay, it looks like, I mean, I could find that very easily. V of 1 would be 1 squared. So that would be 1. So that's going to be the height of that rectangle. Of course, this isn't to scale. But the base length would be 1, which is the width of the interval from 1 to 2. The height would be 1. Okay, and then the third interval against the base is going to be 1. Take a guess at what the height will be. Pause the video if you want to. Okay, and the height, of course, will be 4. So really what I have here is I've got 1 minus 0, 1 minus 0, that's the width of the interval, times v of 0, plus 2 minus 1 times v of 1, plus 3 minus 2 times v of 2, right? That's exactly what I'm calculating here. Now, I don't need that there. I'm just showing you for the details of how I got the values that I did. Okay, so the rectangle that I have in blue with a height of 0, well, that area is 0. I'm going to add that to the red rectangle, which has a base and a height of 1, so the area will be 1, plus the green rectangle, which will have an area of 4. So we would say here that the approximate area under the curve for v of t dt. Okay, for v of t from 0 to 3 is 5. Okay, so this particle, we could say, I mean, I don't know units here. I don't think it gives us any units, but let's say that the units were meters per second for velocity. Then we could say somewhat confidently that our approximation would be 5 meters traveled by that particle. Okay, so let's move to the next slide where we'll do an Rram. All right, here we are on the same function. Okay, v of t is t squared. Let's approximate using an Rram the same area from 0 to 3, v of t dt. Okay, so I'm going to set this up using my Rram method. Now in the Rram method, you justify the height of the rectangle to the right side of the interval. So the blue rectangle will no longer have a height of v of 0, it'll have a height of v of 1. Now you can tell already that this is the value that we'll end up getting will be a value which is an overestimate of the actual. Now I didn't talk about it on the last slide, but the area under the curve from our previous approximation will be an underestimate. Okay, so I can see my rectangle is taking shape. Notice that each of the rectangles' outputs, right, or heights are right justified to each of their intervals. So this will be, this output right here is v of 1. This output right here is v of 2. This output right here, which will be 9, will be v of 3. Okay, so to approximate the area under the curve, we're going to take the width. Okay, so 1 minus 0, that should be in blue. 1 minus 0 times v of 1, right? Plus 2 minus 1 times v of 2 plus 3 minus 2 v of 3. Now it seems methodical that I'm setting these up by taking 1 minus 0, 2 minus 1, 3 minus 2, because yes, all the intervals are 1. However, when it comes to the formal definition of a definite integral later on, it'll make sense why I'm setting it up so deliberately. Okay, so it looks like to me that I will get 1 times v of 1, which is 1, plus 1 times v of 2, which is 4, plus 1 times v of 3, which is 9. So the area under the curve, based on an Rram, would be approximately 9 and 4 is 13, plus 1 is 14. Okay, clearly an overestimate. Clearly. Okay, so let's move on to another method here on the next slide. Okay, this next method is very interesting. This is called an Mram. Mram. Okay, so an Mram is we take each of our intervals, let's go here, right, from 0 to 3. And what we do is we find the midpoint. So this right here would be t equals a half. Okay, the second interval, we would have t equals 3 halves. And in the third interval, we would have t equals 5 halves. Now what we do is we make the height of our rectangle in this method the height of the midpoint. So there would be the sketch of our first interval's rectangle. Our second interval, not my best, that's okay. And then my third interval. You can see that this is going to be slightly more accurate than our previous two approximations, just because you can tell, look, the error is a little off, obviously here, it's almost triangular, but it makes up for it on this side, right? Same thing here, there's some error here, but makes up for it. Error here makes up for it, right? So this balances it out, so to speak, and this is one of the more accurate methods for this particular function. Okay, so the integral, this is called a midpoint rectangular approximation. So again, we're going to have our same setup, 0 to 3, v of t, dt will be approximately. Okay, let's set up our values first. So we'll take 1 minus 0 times v of 1/2 plus 2 minus 1 times v of 3/2 plus 3 minus 2 times v of 5/2. Okay, let's look at these values. Okay, v of 1/2, well, v of 1/2 will be 1/2 squared. Well, that'll be 1/4. Okay, so we would get 1 times 1/4 plus v of 3/2 will be, will that be 9/4? I'm going to square that, 9/4. Okay, so we'll get 1 times 9/4. And then doing a little algebra, we'll do the third midpoint. V of 5/2 will be 5/2 squared, which is 25/4. Okay, so again, we'll get 1 times 25/4. Do a little bit of work. That'll be 1/4 plus, what is that, 9/4 plus 25/4, which will be approximately, well, I know it'll be equal to that, whatever my answer is, but the area will be approximately, what is that, 35/4? I think that's right. Yeah, looks good to me. Which comes out to be about 8.75. Actually, exactly 8.75. I would leave your answer as a fraction. That's fine. You won't be docked for either. Just be careful with rounding as usual. Okay, so clearly we're starting to kind of hone in on the accuracy here. So we started with the Lram, that was an underestimate. We went with the Rram, that was an overestimate. Now with a midpoint, we're not quite sure. Can't really tell overestimate or underestimate. And now we're going to do one more method called the Trapezoidal Method. So let's go ahead and get into that. Okay, let's get into the trapezoidal approximation of the same function from 0 to 3. Let's set up our intervals. Go from 0 to 1, then from 1 to 2, then from 2 to 3. Now, in a trapezoid, I'm going to set up my trapezoid in an odd way here, sitting on one of its, actually sitting on its height in this case. Okay, so let's say these two are right angles, right? So if I were to look at the, for example, red trapezoid, right, these would be my bases, base 1 here, base 2 here, and because of the right angle is the distance, straight line distance between the two bases. Actually, I shouldn't put that in blue. Let's change that color, let's put it in yellow. Okay, straight line distance between two bases is going to be considered the height. Right, it's called the altitude between the bases. Okay, so if I were to sketch the trapezoid for the interval from 1 to 2, right, and if I were to try to form this trapezoid, you can see just how nice and minimal that error is. You can see just that little sliver right there. Okay, so we're going to calculate the area of 3 trapezoids. Now you might say, well, how am I supposed to have a trapezoid in that first interval? Well, a triangle really is a trapezoid. It just has one base of length 0. Okay, so I can see that that is a trapezoid. I've just got a B1, so to speak, of 0 here. I got a B2 of 1 here and a height in between of 1. Here I've got a 1, here I've got a 4, here I've got a 1. Let's look at the third trapezoid here. Okay, you're going to see this portion of the function is very, very much so more linear in its shape than the early portions of the function that are growing so much quicker. Well, I shouldn't say that, are growing in a more curved geometric representation. You can see the curve here and the function here. It's starting to almost look linear, right? And then here, so much more. So the accuracy here is really good. The accuracy here is still good. The accuracy here is not as good. So I'm going to calculate these 3 trapezoids and use them to approximate the area under the curve from 0 to 3 of v of t. Okay, so let's be deliberate about this. And what I'm actually going to do is I'll show you a couple ways to set this up. So we have to utilize this equation 3 times. Okay, so I'm going to take 1/2 b1 plus b2. Okay, so as I look at the first interval, the first base is v of 0. The second base is v of 1. Let's make sure we know where those are coming from again. V of 0, v of 1. Those are like b1, b2. The height is going to be 1 minus 0. Okay, let's do the same thing here for the second interval. It'll be 1/2 v1 plus v2 times 2 minus 1 plus, I'll move this down just for space, v2 plus v3 times 3 minus 2. All right, now I could make this a little bit simpler. I could pull out 1/2 right out of each of them, each of those 3 expressions. And since I know each of these are 1, I could just kind of drop that since I know exactly what 1 times anything is. And I could just add. Now this is the benefit of using intervals that have a width of 1 because it just simplifies things. Okay, v of 0 is 0. V of 1 is 1. V of 1 is 1. V of 2 is 4. V of 2 is 4. V of 3 is 9. And then I calculate. So that would be 1/2 of 1 plus 1 is 2. 4 plus 4 is 8. That's 10 plus 9 is 19. All right, so our approximation for the area under this curve using the trapezoidal approximation method is going to be, what is that, 19/2, which is 9.5. Okay, so I would argue that this is the most accurate we've had so far. So I believe our right rectangular approximation, oh boy, was it 5, I think? Then we had a left approximation, I think it was 14. We knew this was under. Okay, we definitely knew that was under. We knew this was over, right? Just based on the geometry of it all. Then we did the midpoint. We were getting close, right? 8.75. We weren't quite sure on under or over. And now we get this trapezoidal approximation. We get 9.5. And I know this is over, right? So I'm kind of pinning it down, so to speak. We're going to get to the exact methods in later lessons, but this is a very good introduction to approximating the area under a curve. All right, we got one more slide. Let's take a look at it. Okay, let's take a look here. It says to use the Rram on 0 to 5 using 4 rectangles. Okay, so let's use the values in the table to help us to identify a few items. Okay, so it looks like we want to use x values 2 and 3 and 4 and 5. Now, something we haven't encountered yet was negative outputs. We'll talk about those in just a moment. Okay, so let's isolate these by using first 3, 0. This point here has to be the point 3, 0. Okay, so I'm going to just put that kind of off to the side up here, knowing that that's where it's at. Okay, so now proportionally speaking, here would be x equals 2. So this could be the point 2, 3. Okay, again, proportionally speaking, we'll go over 1 unit. This would be x equals 4. So this point here should be the point 4, -2. And then one more point. Here's x equals 5. And this point would be the point 5, -5. Okay, so let's do an Rram, okay, with 4 rectangles. Okay, so I'm going to go from 0 to 5 using 4 rectangles. Well, here's x equals 0. So my Rram, I right justify my rectangles. So my first rectangle is going to be on this interval. And because I right justify, that means I use the output for the very right point on that interval, and then I create my rectangle. Okay, so that first area, that first rectangle, 0 to 5, f of x dx, okay, is going to be, let's go with the base, which will be 2 minus 0, times the height, which will be f of 2. Okay, plus, now I right justify on my next. Here's my interval, here to here. Looks like the output for the rightmost point is 0. So I'm going to go 3 minus 2 times f of 3 plus, okay, my next interval, here to here, my rightmost point gives me an output down here. So now this area, okay, this area will actually take on a negative magnitude. Any area below the x-axis, right? As long as we're moving left to right, we'll take on a negative magnitude, and you'll see it take form here in just a moment. So let's take x equals 4 minus x equals 3, of course, a width of 1 times f of 4. Okay, our last rectangle we'll do in purple. Okay, so here's our interval, 4 to 5. Our output will be f of 5. There we go. So we'll take 5 minus 4. There's the base of the rectangle. The height of the rectangle is f of 5. Okay, let's do a calculation. 2 minus 0 is 2. Now you'll notice that the widths of each of these rectangles are not all the same. That can sometimes happen, so be prepared for that. F of 2 is 3. Don't make the assumption that you'll always have equal subintervals. Okay, base on the red rectangle is 1, 3 minus 2. F of 3 is 0. Okay, again, you might be asking, why is he writing all that out? Because you should get used to it. Okay, it's the technical setup for this approximation method. F of 4 is -2. And then the final rectangle, base of 1, output of f of 5 is -5. All right, so as we add these together, I get 6 plus 0 minus 2 and minus 5. So the approximate area under the curve, in this case, of course, we can't necessarily say that our output should be negative for the area under the curve. It's all dependent, right, upon the orientation of the function, but we're going to approximate that to be -1. All right, Let's continue to the summary and a couple of notes before we wrap it up. Okay, so there's 3 ways we can approximate the area under a curve, and actually 4. We touched on the 4th, which was trapezoid, but in this summary, we're just going to talk about the 3. Okay, there's 3 ways, like I said. Number 1 is an Lram, right? So we're going to approximate we're going to calculate our rectangle from the left side. And so as it says here, use rectangles that touch the curve on the left side of the rectangle. Number 2, Rram. Number 3, midpoint. Okay, we're going to talk about Lram and Rram and how those overestimate or underestimate and in what cases. So I'm going to draw 4 curves. I'm going to draw concave up increasing, concave up decreasing, concave down increasing, concave down decreasing. So let's do concave up functions first, like the function we just looked at, right, t squared. When we did our Lram from 0 to 3, looked like this. All right, clearly an underestimate. So if we have concave up increasing, it's going to be an underestimate. It being the method that we're using, which is an Lram, right? Concave up increasing, underestimate. Okay, let's draw a second. Let's go concave up decreasing. Okay, a function like, I don't know, 1 over x or 1 over t. If I did an Lram, let's say from 1 to 4, our rectangles would look like this. That's an overestimate. So concave up decreasing will be an overestimate. Concave down increasing, a function like, let's say, the square root of x. That's concave down, or the square root of t. That's concave down increasing. Lram, right? Clearly underestimate. Concave down decreasing. Might be a function like this. I don't know what that function would be necessarily right here. But whatever, I don't need a name for it. Let's look at the Lram here. Okay, I could go from 0 to 3, 1, 2. Clearly that's an overestimate. Over. Okay, let's look at a right Riemann sum and how we determine under or overestimate. Okay, so again, let me actually do these on the sketch above. I'm going to do an Rram on each of the sketches. So we'll start top left, t squared, right? We knew that. Concave up increasing was an overestimate. Concave up decreasing, right Riemann sum, looked like this. That's an underestimate. It's kind of a complement of all of these above for the left Riemann sum. Okay, square root of t with a right Riemann sum would look like this. Clearly an overestimate. And finally, concave down decreasing, underestimate. Okay, for midpoint Riemann sum, we don't know whether the approximation is over or under. So we're going to leave it at that. And we haven't seen AP ask a question about approximations and over or underestimations with midpoint at this point. But if they do, we'll get it in here and we'll make sure you're aware of it. All right, guys, that's it for 5.2 day number 1 on approximating area under the curve. See you next time.